Hi everyone, welcome to week 10. This is the final week that I will be going over any problems within tutoring of the PSU Learning Center for Chemistry 222. I will also not be tutoring next term, so this is my last time for now. So let's get started. This is going to be week 10 material, so we are going to be going over chapter 13, which includes like constants of reactions and also Le Chatelier's principle, which has to do with equilibrium reactions and the way they'll shift depending on how much is going on with the reactants and products and things like that. So let's get started. This is question 57. So this one asks, when heated, iodine vapor dissociates according to this equation. So iodine gas to 2 iodine of gas, but it's just I. At 1,274 Kelvin, a sample exhibits a partial pressure of I2 of 0.11228 atmospheres and a partial pressure due to iodine atoms of 0.1378 atmospheres. Determine the value of the equilibrium constant, Kp, for the decomposition at 1,274 Kelvin. Okay, so in this problem, we first have to identify kind of like a generic equation or a reaction. And the reason why we will do this is so that when we use the equation to solve for the equilibrium constant, we know what to plug in for. So kind of a generic equation form will be like so: Ma plus Nb goes to Xc plus Yd. And so the M and the N and the X and the Y are all just coefficients, and the A and the B are different, and C and D are all the different kinds of species of molecules or atoms or anything like that. And the A and the B is going to be the reactants, the C and the D are going to be the products. So just as we know the kind of like the formula of like a basic reaction, let's find or use the equation to solve for this problem. So we need to find Kp. And Kp, the equation for that is going to be Kp equal to the products. And we're working with pressure here, so it's the pressure of all the products raised to the coefficient, and then multiplied by each other. And then all divided by the reactants that are also of their pressures and raised to their own coefficients and multiplied by each other. Okay, so this is the equation to use for finding the Kp. All we have to do is just plug in these values. So we're given I2 gas goes to 2I gas. And so this will be the product. So that goes first. And so since it's alone, we just will leave it alone there. So it'll be I, P, and it'll be raised to the power of 2 because of this coefficient. And then divided by the reactant, which is just I2, its pressure. And it doesn't have any coefficient, so it's not raised to any power. So when we plug in all these values, we'll plug in the 0.1378 for the iodine atmospheres that it gave right here. And then the 0.1122. And the top one is raised to the second power. And so when we multiply that out, we will get a Kp constant of 0.692 as our answer. And so that's how we will be kind of going over these problems, is, you know, figuring out what we need, setting up the equation, and then maybe algebraically solving for whatever we want to find for. So if like we wanted to find one of these, we would have to move things around to find the partial pressure of C, for example. So let's move on to the next problem. Let me know if you have any questions as well. Okay, this one says, calculate the number of moles of HI that are at equilibrium with 1.25 mole of H2 and 1.25 mole of I2 in a 5-liter flask at 448 degrees Celsius. So, just as I was talking about previously, sometimes we will have to algebraically solve for something in the equation. So we are given the constant, and now we are working with molarity. So because we're working with molarity instead of pressure, we will just be putting in the molarity of each of these values. So the basic equation that we were talking about earlier would be Kc equal to the products on top, so that's the Hi. But since it has a 2 coefficient, we'll raise it to the power of 2. And then divided by the reactants, so that's I2, it's concentration, there's no coefficient, multiplied by H2. And now all we have to do is solve for Hi, because that's what we want to find in this problem. It asks for the moles of Hi. So let's rearrange this equation to solve for it. And so let's multiply both sides by this thing right here. So it'll be Kc times I2 times H2. It'll be Hi squared. And then I'm just going to switch this round. So put this over here since I like to solve for things on the left. And then if we square root this, then we can solve for the molarity of Hi. Okay, so now we have the equation to work with to solve for all of these. But in the problem, it only gave us moles of H2 and moles of I2. But it did give us the volume. And remember that the concentration will be equal to moles per liter. So for each of these, we will just divide, or we'll have the moles per liter. So it'll look like something like this. Kc, let's put that constant in. So 50.2 times I2 concentration. So that's the moles of I2, which is 1.25, divided by the 5 liter of solution. And then it's going to be the same thing because there are the same amount of moles of H2. So it's 1.25 divided by 5. And then we can square root this entire thing. And so when we divide everything out, we will get an answer of, let's see here. Let's do this on my calculator first. So 1.25 divided by 5 times by the same thing, times by 50.2, and then the square root of that. So we will get an answer of 1.7712989584. But this is in moles per liter. And it did ask us to only find the moles of Hi. So the moles, what we would have to do is take this value, 1.7712989584, and since it's moles per liter, multiply it by the liter amount, which is 5 liters, and then we will get an answer of 8.86 moles of Hi. So that's how we solve this problem. Sometimes it's tricky with the terminology if they're asking you for moles, but you accidentally solve for molarity instead. It's always good to double check, making sure that you're solving for the correct thing. Okay, let us move to the next problem. Okay, so this one says, what is the pressure of BrCl in an equilibrium mixture of Cl2, Br2, and BrCl if the pressure of Cl2 in the mixture is 0.115 atmospheres and the pressure of Br2 in the mixture is 0.45 atmospheres. So we are solving for the partial pressure of the BrCl. So let's set up the equation solving for the Kp constant, and then we can move things around to solve for this term, specifically in the equation. So what that looks like is Kp, similar to the ones, or the same setup as we did with the previous questions. And so that's going to be equal to the products on the top, so that's going to be the BrCl. And this is partial pressure instead of concentration, so it's partial pressure in the bottom, or a subscript here. And it has a 2 coefficient, so we will raise this to the power of 2. And then we are going to divide by the reactants. So the reactants are Br2 and Cl2. And they don't have any coefficients to them, so we don't have to raise them to any power. Okay, so that is the equation set up. And so since we have to solve for the BrCl, it's going to be right here. Let us move some things algebraically around to get that isolated. So let's first multiply by this bottom term here. So we will get Kp times Br2P and Cl2P. And then that will be equal to BrCl P squared. And so I'm going to switch things around because I like to solve for things on the left. So this will be BrClP. And so since this is squared, I'm going to just find the square root on both sides to get rid of it. So it'll be the square root of the Kp times Br2P Cl2P. And so since we solved for it, now all we have to do is just plug in the values from the from the problem that it gave us, and then we can find the answer. So the Kp value is going to be 4.7 times 10 to the negative 2 times the partial pressure of Br2, which is going to be in the problem 0.450, and then times Cl2 partial pressure, which is 0.115. And so solving for that, we will get an answer of 0.0493 atmospheres. Okay, so let's move on to the next problem. I will leave that up for a second while I go over what I have prepared for you all. Okay, let's move on to the next problem. So this will be problem 77. And this reads, what are all the concentrations after a mixture that contains water at 1 molarity and Cl2O at 1 molarity comes to equilibrium at 25 degrees Celsius? And this is the Kc constant. So it is asking for the concentrations after a mixture. So it's asking for the mixture after it contains this. So basically, it's trying to use different terminology to tell you what is the product concentration. So we're going to be finding this concentration. And so let's first set up the equation for the constant, just as we did. So Kc will equal the products on top, so that'll be the HOCl. And we are working with concentrations here, so it's concentration brackets. And then this will be raised to the power of 2 since it has a coefficient. and then divide everything by the reactants multiplied by each other. So we have H2O concentration multiplied by Cl2O concentration. And so when we plug all these, before we plug any of these values in, we need to solve for the concentration of the product. So let's do that. So let's multiply both sides by this right here. So it'll be equal to Kc times concentration of H2O times the concentration of Cl2O. Okay, and now let's switch sides like we did. It's a little better on the eyes. HOCl. And so I'm going to square root both sides as well. So it's 2 in 1 step. Okay. And now let's plug in our values. So Kc was at a value of 0.0900. Water was at a concentration of 1, and same with Cl2. So it'll just be the square root of the Kc value, really. And that will have an answer of 0.3. And this is in molarity, since we're finding the concentration of HOCl. Okay. So let's move on to the next problem. I will leave this up for a second if you want to look at it. Okay, let's move on to the next problem. This one says butane exists, this is problem 80. And it says butane exists as 2 isomers, N-butane and isobutane. So it gives us the Kp constant, and it's asking for the pressure of isobutane, so this one right here, in a container of the 2 isomers. So the 2 isomers is going to be the N-butane and the isobutane at equilibrium with a total pressure of 1.22 atmospheres. So this problem is a little bit different because it doesn't give us the direct equation for the N-butane and isobutane in not this form of like what it looks like and with the bonds, and it also doesn't tell us the individual partial pressures. It only gives us the total pressure. So what we will have to do is kind of solve for what it will be, so that the N-butane and the isobutane, and then plug something in to solve for it. And what I mean by that is when we have this equation right here, so Kp will be the constant, right? And we'll have the products on top, and so that I'm just going to, this will just be iso. I'm just going to abbreviate it, and the bottom one will just be N. So iso would be on top. And and before we move any further too, there doesn't need to be any coefficients. This is completely balanced. There's the same amount of carbon here on both sides and the same amount of hydrogen, so this is balanced. So regarding that, there's no raising to anything of the power. And so the equation will look like this. And it gives us the Kp constant, so that would be 2.5, right? But we don't have any individual values, but we can use the total pressure to try to figure out in terms of the other isomer to plug it in. So we know that the P total, so the total pressure, has to be equal to the pressure of NP and iso-P. So if we just solve for one of them, in this case, I would like to solve for NP, because if we do, we will isolate what we want to find, which is finding the pressure of iso. So if we solve for NP, we just divide or subtract it. So P total is going to be minus isop. And so now we have an equation for NP in terms of isop. So now we can plug this in. So right here, this will go right into here. Right in here. And so that'll be equal to isop divided by P total minus isop. And so that'll be equal to the constant as well. So now we have it in terms of isop, and we can algebraically solve for the isop by itself, and then we can solve for it and plug in the terms. Or actually everything is plugged in, so all we have to do is just isolate isop. So I'm going to bring this down here as well. Okay, so if we multiply both sides by this right here, it'll look like this. So isop equals 2.5, and the P total here, let's just plug it in, will be a value of 1.22. And so if we multiply both sides by that, and there we go. So let's multiply it. So that's going to be, let's see here, 3.05 minus 2.5 isop, and that'll be equal to isop. And so now all we have to do is get the isops on one side and then solve for it. And so when we do that, we will get, so we'll add both sides 2.5. So we'll have 3.5 isop equals 3.05. And so dividing both sides by 3.05, we will get an answer of the partial pressure of isobutane as 0.871 atmospheres, because we are in the units of atmospheres. So that's the final way of solving this. It's a little tricky at first because, you know, it doesn't give you the direct individual values. And so because of that, then you kind of have to figure out and use a substitution equation to then solve for it. Okay, now let's use this equation. And I will let you look at that for a second. I will be right back. Sorry about that. Okay, so now let's solve this problem. So the goal is to teach, somebody said in the chat, why don't you save your videos? I do actually. This is all going to be posted to the PSU Learning Center's YouTube channel. So all these recordings will be posted there as well. So these are the live recordings if you want to ask questions like now. But then all of this will be recorded and posted to that. So I can link that in the chat if you'd like to look at those videos. Yeah, let's go over this problem. So this one says, suggest 4 ways in which the concentration of hydrazine and 2H4 could be increased in an equilibrium described by the following equation. So we have N2 plus 2H2 goes to the hydrazine. So just looking at this problem, we have 2 reactants and we have a product. So, and it also gives the enthalpy for this reaction. Oh yes, what did you say? Sure. There's a setting. Oh, gotcha. I would want to say them. I don't have Twitch Prime. I could have it saved each week. I actually did not know that was an option to save them on Twitch. So thank you for letting me know. I wish I knew that earlier, but this is my last week teaching the chemistry tutoring for this term. So I'll pass that along to other people that are with the Learning Center and teaching through Twitch. So I'll let them know. Thank you for letting me know. Okay, but let's go over this problem. So if we want to increase the concentration of the hydrazine, what we can do is, one of the best ways of doing that is just increase the reactants. So increase the moles of N2, for example. And then also following that up is to increase the reactants of the other one, or the other reactant. So increase moles of the H2. And so when you increase the reactants, and they're on the left side here, you will increase production because you'll have more of basically your recipe, and because you have more of your recipe, it'll want to be used up more. So because of that basis, then it will want to make more of the product of the hydrazine. And so the other way it can be increased, this concentration can be increased, is to decrease the container volume. And when you decrease the container volume, it proportionately also increases the production because it's in a smaller container. So you will therefore have more heat going on, and if you have more heat, more of this hydrazine will be created because this enthalpy is positive. So because the enthalpy is positive, you have to put in energy to create the product, the hydrazine, and so it needs more heat. So if you have more heat, therefore you need to decrease the volume of this container. So that's the way that works here. And then for the fourth way that you can do is just increase enthalpy, increase the heat. And so for the same exact reasons, that's another way you can increase the concentration of hydrazine. Okay, let's move on to the next problem. Okay, so this one is 38. It says, how will an increase in temperature affect each of the following equilibria? How will a decrease in the volume of the reaction vessel affect each? So for the first one, we have 2NH3, and it has two products, nitrogen gas and hydrogen gas. And there is a positive enthalpy going on. And for C, problem C, we have one reactant and one product, and it's negative in its enthalpy, meaning that it's going to be releasing the energy and lowering its state. So it's more preferable. Yes, yeah, Chuck, I'll definitely do that. Thank you for that future reference. I will take a screenshot and make note of it. Thank you. Okay, and so since the first one is a positive enthalpy, that will change the way that decreasing and increasing the volume and temperature to affect like what's going to be happening. So let's just get started in answering these questions. So when we increase temperature and then decrease temperature or decrease volume. So I'm going to just pull these down here. Get it set up for us to answer. Okay, so when we increase temperature for this one, we are going to shift right. It's as simple as that, because we are increasing the temperature, which is more likely to make more of the products, because we'll have more energy needed, and because this is a positive energy, it'll need more energy to make the products. And so since it's giving it to us, then it'll proceed with making the products. And so when we decrease the volume, oddly enough, it's actually the opposite, because we will be shifting left. Because unlike the last problem here, when we increase or decrease the volume of the container, we increased the production of the N2H4, and it was a positive enthalpy. And so because of that, then we were able to increase the concentration. But here, with this problem, this one's on the left. So when we decrease the volume, we will actually be... Put this over here. Sorry about that. We will actually be shifting to the left, because now we're decreasing the volume, we have enough energy, but we want to make more of the product now, or not the product, the reactant, which is going to be this. And so then we will be shifting left because of that. Okay, so now let's move on to the next reaction here. And so when we increase the temperature here, we will actually be moving to the left, because this is a negative enthalpy. And so when it's moving to the right, it's releasing energy. But when we're moving to the left, it's putting in energy. And so when we increase the temperature, we have enough energy, and so it's going to want to make more of the reactant. It's going to want to go the other way. So it's going to want to shift left. And so when we also decrease the volume, it's going to want to shift left as well, because now it has more energy to make the reactant. And because moving to the left needs energy, we'll have energy, and so we can make it then. So it's going to shift left. Okay, so now let's move on to the next problem. I'll leave that up for a second if you're still looking at it. Okay, so this one's a big problem. I'm going to zoom out a little bit and maybe make this a little bit bigger so you can see better. Okay. So 40 says, methanol can be prepared from carbon monoxide and hydrogen at high temperature and pressure in the presence of a suitable catalyst. It says, write an expression for the equilibrium constant, Kc, for the reversible reaction. Okay, so this is going to be just as what we've been doing before. So when we find the equation for Kc, so Kc is going to be equal to the reactants, or sorry, the products on top. So that will be the CH3OH. And this is going to have the concentration, not the partial pressure here. And so then divided by the reactants. So we have H2, and that'll have a exponent of 2 since it has a coefficient of 2 in the reaction. and then multiplied by the CO concentration. And so that is the generic form of finding the equilibrium constant. So that's all it is asking for us in problem A. So let's move on to problems B. Okay, so it's asking what will happen to the concentrations of H2, CO, and CH3OH at equilibrium if more H2 is added. So before actually we answer these problems, there is just a standard kind of way of or standard thing that's happening. What will happen with H2 and CO is if you increase one of the reactants, the other one will want to go down because they want to balance each other. So that's kind of like a standard way or a standard concept for these. So H2 and CO want to be balanced. Okay? So, and the other things is that if we increase reactants, it's going to want to create more products, given that it's going to release energy. So it's releasing energy in this problem, so it wants to make more of the products. So when we increase the reactants, it's going to want to make more of the products. So adding reactants increases product. And then vice versa, when we take away more of the reactants, the product amount will go down as well because we have less to work with in the beginning, so we can't create as much because we're lowering the concentration, we're lowering the amount. So reducing reactants reduces product. And then when we add product, it's going to also increase reactant because it's the same way. It wants to balance each other. It wants to make more. If one's too much on one side, it wants to balance that. So it needs to add more on the other side. So when we add products, it's going to add reactants. Okay? And so now let's answer these. So for B, it says what will happen to the concentrations. And actually I'll put the H2CO goes to CH3OH. So that's the reaction. So we can look at that for notice. Okay, so B, what will happen to the concentrations of H2, CO, and H3OH? So all of the things in this reaction, each term, at equilibrium if more H2 is added. So H2 is a reactant. So when we are increasing the reactants, just as we were talking about before, kind of our rules to follow, is that the reactants, the two reactants in this problem are going to want to balance each other. So if you increase one reactant, the other reactant will reduce. So H2 is obviously going up, so it's being added. So H2 goes up in this reaction. CO goes down, but since we're going to be increasing the amount of H2, we are also going to increase the amount of the product because we're increasing the reactants, or the reactant singular. So we are going to be increasing the product here. So now for C, it is asking if CO is removed. So CO is going to be the reactant. And so if we reduce one of the reactants, if we're reducing one of the reactants, we're going to increase the other reactant. So they will have to balance each other. So we're going to increase H2 as well. But then CO is being removed, so it's being decreased. But the product is going to be decreased as well, because you're decreasing the reactants, or the reactant, singular, you're going to reduce the product as well because of it. And now let's look at D. So D is asking if the product, CH3OH, is added. So we're increasing the product. And so when you increase the product, you increase the reactants. So everything in this situation is going to increase, actually. So the reactants are going to be increased because more of it's going to be need to be balanced for that reason. And you're adding CH3OH, so that's obviously going to go up. Make these arrows a little bit more clear. Okay, and so now let's move to E. So E says what will happen if the temperature of the system is increased. So if the temperature is increased in this problem, what will happen is that, so since, like I said before, the enthalpy is negative, so that means when it's going to the right, when it's proceeding to the right, I think on your case when I'm going here, it's going to the left. So when it's going to the right, that means that it's going to release energy. So in problem E, it's saying if we increase the temperature. So if we are increasing the temperature, we're given some energy. So we don't need to go to the right anymore because we actually need to go to the left. And so the problem will shift left because now it needs to go the other way since it'll have the energy needed to make more of the reactants. So it'll shift left. And then for F, this is the last problem of the day. It says what will happen to the concentrations of H2CO and CH3OH at equilibrium if more catalyst is added. So if more catalyst is added, nothing will actually happen here because it's already going to be releasing energy since the delta enthalpy is negative. And because it's negative, it's already going to be releasing energy, so nothing will actually happen here. So there's going to be no change in this problem. And it's also asking, not only is the enthalpy going to be like that, it's asking for the concentrations. So the concentrations will not change at all. What a catalyst does is it just speeds up the process of the concentration being made, but it doesn't actually change any of the concentrations. So that's also tricky to know that, it doesn't really need it here. But, sometimes you do want to have a catalyst. You want more production to be made. And so that's good. But it will not change any of the amounts of anything. It's just how fast it'll change things. Okay, so that is the last problem. I'll leave that up. So let me know if you have any more questions on any of this material I went over today. Thank you for listening, and as always, this will be posted to the PSU Learning Center's YouTube channel. I will, in the future, if I stream with the Learning Center again, I will be sure to post it also to Twitch and let other people know about that. And besides that, thank you all for listening into my videos for ever since last fall. This is my last time streaming today, so it's been a great time helping you all with chemistry. Yep, of course. Other than that, good luck with your finals if you have any, and goodbye for now.